Yeah, so I'll briefly introduce Ian. Ian Beausoleil-Morrison, he's Professor of Engineering at Carleton University. He has been quite a figure within the IBIPSA community, which is the worldwide international building performance simulation association community. We have conferences every 2 years. And nationally, we have our local chapters, for example, IBIPSA England, in which I'm very active, and IBIPSA Canada, US, etc. So we have local chapters that also run their own conferences. So Ian was in fact president of the society from 2010 to 2015. In fact, I thought you were president until much later as well, but Ian has always been very active in the community and with respect to his contributions. And as a result of it, he is fellow of the society, as well as elected or nominated fellow, as well as receiving the Distinguished Service Award, which is one of the highest awards within our community that's given to individuals that have contributed to the field. At Carleton, Ian runs the Sustainable Buildings Lab. He's going to talk about his research there. And he's also one of the key things that Ian does also is co-editing the main journal of our society, which is the Journal of Building Performance and Simulation. So delighted to welcome you here. And yes, over to you.
Okay, thank you very much, Ruchi. So what I'd like to talk to you about today is teaching of building performance simulation. So I won't be getting into my research work, but instead talking about methods that I use for teaching the topic of building performance simulation. And I'll talk as well about the book that I've authored that supports that teaching approach. Maybe a quick show of hands from people who use building performance simulation tools or have used it in their work or their research. Okay, so a few of you. So building performance simulation tools, it's changed drastically over the last decades. Nowadays, users of BPS tools have a choice of numerous tools that look very well. They are very sophisticated and well developed and well supported. And that's radically different than the situation 30 years ago when I first got into the domain. We have tools like ISVE and Design Builder, which are commercial software used pretty extensively by practitioners in the industry. Tools like eQuest and Open Studio and Energy Plus. There's dozens and dozens of tools. There's probably at least a dozen or 15 that are used fairly extensively around the world. And they look quite slick and sophisticated. And a lot of the developers of these tools will make fairly bold claims like you don't really need to be an expert in building simulation to use our tool, or our tool makes it easy. And it's true that they make building performance simulation much more accessible. When I got into the domain over 3 decades ago, we were preparing text-based input files. So there was no graphical user interface. There was no feedback and results analysis, for example. But that said, there's a statement made by one of the pioneers in our field, Linda Laurie, who used to work on the BLAST program in the US and then the Energy Plus program. She made this statement almost 4 decades ago, talking about how the user is the main source of uncertainty in building performance simulation tools. And I think that's still the case today, despite that we have these developed user interfaces, much more accessible tools. User is still the main source of uncertainty. And I'll provide you a few examples of why I think Linda Laurie's statement is still pertinent today. I would say using these BPS tools is actually really easy. You can put the tool in the hands of a novice user, and within a few days, they're able to push all the buttons, pull all the levers, and get the tools to produce some simulation results. But producing accurate results remains very challenging. This is an example from my own teaching. So full disclosure, these are all brand new users of the tool. Each one of these bars represents an individual student result. They're predicting a space heating load on a very simple building. Here's where the correct answer is, plus or minus 10% of the correct answer. And you can see they're all over the map. But every one of these students was able to operate the tool very easily. This is within 2 weeks of the beginning of the academic semester. They're all able to produce a simulation result. but the results are all over the map. So you can look at that and say, yes, they're novice users. Maybe I didn't do a good job teaching them. That's understandable. But if we look to the literature, we see that this is a result that we see time and time again. This is one of the earlier studies that was looking at the sources of error in building performance simulation predictions out of France. There were 12 users using the exact same simulation tool, all fairly extensively trained and professionals using the tool, and they produced results all over the map as well. Here's another example from California from about a decade ago, where 12 professionals who earned their living performing building performance simulation work for paying clients were given the same set of drawings and specifications for building and asked to predict results. And the yellow line here is the correct result. They were asked to predict monthly gas consumption and monthly electricity consumption. And you can see the results are all over the map as well. The spread is almost the same as we see in those novice students. Here's another example from an International Energy Agency project where there's a black line here that represents the measured performance of a research facility, research house. And 21 teams, mostly PhD and postdoc students, were using different simulation tools to predict the performance of that building. And again, we can see a pretty big range of results in those predictions. So I think this really supports that statement that Linda Laurie made almost 4 decades ago, that the user still remains the main source of uncertainty in using these tools. And there's lots of reasons why. It is actually a fairly complex problem to be able to predict the performance of a building, because in any building, here's just one example, we have a number of interrelated heat and mass transfer processes happening. So we have convective heat transfer, radiative heat transfer between internal surfaces, transient conduction happening in wall assemblies, air infiltration. All of these individual processes have to be represented with models, and they all have uncertainty associated with them. But it's also easy for users to feel overwhelmed in using these tools. Most of these tools provide default inputs, default modeling options. And in many cases, the users just feel overwhelmed. They don't know where to focus their efforts in using these tools. And I've been trying to teach people how to use VPS for 30 years now. And some of the methods I've tried have worked reasonably well. Some of them failed terribly. And I've tried to learn from my mistakes. And I've really decided that really the best approach for teaching people these simulation tools is to forget about the tool itself and to teach them the fundamentals of what is the tool doing internally? What are the algorithms applied by the tool? What are the default methods, the default assumptions, and the implications of using some of those defaults? So I really focus now on teaching these fundamentals and looking at the theory behind the tools. And my belief is, and I've seen this happening, is once the students understand the fundamentals, or people understand the fundamentals, they can pick up any one of these user interfaces that are available, and they can effectively employ them afterwards. So I've been teaching this topic at Carleton University for a number of years, and every year I develop more and more extensive course notes. And I decided when the pandemic happened, I was locked into my house for a period of time like everybody else. I thought, well, I might as well turn these notes into a book. So that was my pandemic project. So I've written this book that was published 4 years ago. And my focus in the book is really on understanding the depth of what VPS tools are doing, rather than trying to cover all of the bases. So I'm really focused on heat and mass transfer processes happening in the building. There are aspects of building performance that I just simply don't touch. I don't have the space to deal with it. Things like acoustics and hydrothermal modeling and indoor air quality. But I've written this book and my teaching method on the presumption that the people working with it have a basic understanding of heat transfer and thermodynamic processes, a little bit of understanding of psychrometrics, a little bit of understanding of building HVAC systems, but they're not experts in these areas, and they have no previous experience at using VPS tools. And the way I've structured the book, it's structured along the methods I've used for teaching, is that it's broken up into a number of chapters, and each chapter is dedicated on one topic. Most of the chapters are on a single heat mass transfer process, say air infiltration. So for each of these topics, there's some theory that describes the physical processes that are happening, the types of models that have been developed in BPS tools for representing those processes. So the reader understands some of the theory of what's going on inside the tool. And then immediately there's simulation exercises that are pertinent to that topic, that heat or mass transfer process. So they perform that in any simulation tool they choose. And when I teach the course, I have the students perform the simulation exercises. They submit the results to me, and then when we come together the next class, we do what I call an autopsy. So we basically dissect what they've done. We pull it apart and we try to understand why one person had a result that was very different than the other people. We try to understand the reasons for that. And then once we've been through that topic, this is what I encourage the students to do, is reflect on what they've learned, go back to the theory and understand why did the simulation tool predict a certain result, and how do they relate that to the theory? And once we've been around that topic circle, we then move on to the next topic in the book. And again, the book is written around the approach that I use for teaching. So what I've done is broken the building up into a number of different segments or parts. The first part of the book has several chapters that treat all of the processes that are happening within the building interior. So that could be heat gains from occupants, moisture sources from occupants, radiation exchange between internal building surfaces, where passive solar gains that have passed through the window are absorbed and how they're absorbed on surfaces. The next part of the book treats all the processes happening between the building's exterior surfaces and the outdoor environment. So that could be long wave radiation to the sky, heat transfer to the ground. And then it looks at what's happening within the building envelope. So that could be transient conduction through wall assemblies, air infiltration, solar energy transferred through a glazing assembly, and then HVAC after that. Yeah. So each chapter and each lecture I give to students is broken up into a similar structure. There's some theory, and that theory depends on the complexity of the topic. It might only be half a dozen pages, or it might be 20 or some pages. And that really touches upon the methods that are commonly used in BPS tools. So it's not related to a specific tool. It's talking about the breadth of methods that are used in various tools. And it talks about the strengths and weaknesses of the models. And in many tools, the user has a choice between different modeling methods. So they develop an understanding of the strengths and weaknesses of them. And then for the students who want to delve into greater depth, there's some guidance for further reading. So usually these are references to journal articles, and I'll guide the student to read a certain section of the journal article and what information to look for from that. And then there's simulation exercises in each of the chapters. So for example, here's an example of the treatment of theory on long wave radiation exchange between the internal surfaces of the building. So we want to understand what methods are used by tools for predicting the radiation exchange from this surface down here, this wall surface, to this wall surface up here. So again, it presumes that the reader has a basic understanding of heat transfer fundamentals, but it does review things like emissions from black body, emissions from gray body. It develops a theory for radiation exchange within a gray enclosure. And it shows the development that's used in some tools, how that heat transfer quantity is actually calculated. And then you can see from that radiation view factors between individual surfaces are necessary. So then this is only used in certain tools, but then the reader of the book will use their simulation tool they've chosen and see, well, what options are available in that simulation tools for calculating these radiation view factors. And then realize what parts of that equation they need to provide data input for, and what is default. Here's another example on the treatment of theory. In this case, this is solar energy absorbed by external surfaces. So a lot of the students who take my course and get into this BPS domain might not understand things like solar angles. So a little bit of treatment of that so that they can understand what's the geometrical relationship between the sun position and a building surface. And then it discusses how it's common in BPS tools to calculate that solar energy absorption on an external surface as a sum of three components. The beam component that's traveled directly from the sun without scattering, and then the sky diffused scattering component, and then ground reflected component. And then it talks about the theory that's used for calculating each one of those. So it discusses, for example, methods that are used for predicting sky diffuse. And all building simulation tools have some embedded models for calculating the sky diffuse. What most users of tools don't realize is these are entirely empirical models. They've been tuned for particular locations on the Earth. So the reader will understand the structure of the different sky diffuse models that have been developed and what are the strengths and weaknesses of the different models. I mentioned there's exercises done with each topic, and then the students will perform those exercises, submit the results to me, and then I graph them and share the comparison of those results when I meet with the class. And then we'll ask individuals to come up and volunteer to plug their computer in and show their work to the others. These exercises are written to be tool agnostic, so they've been performed with about half a dozen commonly used building simulation tools, some not commonly used, but about half a dozen building simulation tools. And here's an example of one of the autopsies or some of the exercises plus the autopsy result. So most of the exercises are really simple to perform. They're based on a simple shoebox building representation. And then for each exercise, there's minor perturbations from those inputs. So this exercise here, the user will alter the solar absorptivity of just one surface. So take that floor, and instead of having a solar absorptivity of 0.9, they'll change it to 0.6, or the other way around. And we'll see what impact does that have on simulation predictions. So here's an example of a student submitted result where we're looking at the heat absorption rate on the floor surface over a single day. And they can see right away this makes sense from a theoretical perspective of their understanding of the theory of the radiation heat transfer. When they increase the absorptivity of the floor surface, there's more energy absorbed on that floor surface. So that result reinforces what they've learned from the theory treatment. But then they look at what impact does that have on the building heating? And they can see on this student's result, they see right away, well, almost zero impact. So we have a discussion then, and then usually students will contribute to those discussions and understand, well, why does that increasing the absorptivity increase the amount of solar absorbed on the floor, but has virtually no impact on the building heating load? And they'll come to the realization then, well, it doesn't really matter so much in most buildings which surface absorbs the solar energy. It's inside the building envelope, and it's going to be redistributed to other surfaces through long-wave radiation exchange or convective heat transfer. So they develop an understanding from this that determining that quantity, that solar absorptivity, is usually not that critical in the building simulation analysis. So that's information that they use to build up their experience. Here's another example on air infiltration, where we have an exercise where we alter between two commonly used methods in the VPS field. Despite how sophisticated some of those tools are, when it comes to treating air infiltration, most do it very simplistically. It's common for those tools or users to just completely ignore air infiltration. So we have no air transferring from outside to in through random openings. And another common approach is to prescribe a flow rate. So we'll contrast those two simulation results. And that's what we see, different student results here, and they're contrasting that simulation prediction on space heating mode. And they can see right away, well, that has a big impact on space heating results. That's far more significant than getting a solar absorptivity right. And then some tools will have more advanced models, so they'll try out those more advanced models and tools that are available. So as they go through my course or my module and the book structure as well, they're performing exercises on individual heat and mass transfer processes. And then we put it all together towards the end, and we perform what I call culminating trials. So now they're going to take the knowledge that they developed through simulation and apply it to a real building. And this is my research facility on the Carleton University campus. It's looks like a house. It's an unoccupied research facility that's quite heavily instrumented. And I'll give the students all the building plans and specifications for that building. They've got access to photographs during the construction phase, so they can understand that there's a hydraulic floor heat distribution system. They understand the materials that are used for constructing the building envelope. They get scale drawings, they get details on internal heat gains. There's a weather station on site, so they get access to the weather data on site. And then they're asked to predict the performance. And this is now where every student will go off in different directions, and there's great learning value in that. The students in my module are using different tools, tool of their choice. And some of them are taking more simplified approaches, some are taking more detailed approaches. Time is finite, so I tell them how much time they should spend on this project. And they have to decide how to allocate the time. Do I spend time on trying to represent the infiltration heat transfer as accurately as possible, or do I spend time searching for data on solar absorptivity? Do I spend time representing the details of the geometry? Here's a couple of examples of what students did in the last time I offered the module. One used a design builder tool, and she spent a great deal of time faithfully representing all the geometric details. So she spent a lot of time. Everything from the small closet spaces in the tool rooms within the facility were represented explicitly. Each window is explicitly represented. Here's another tool a student who used the transit simulation tool, and he took a much more simplified approach. He said, I don't think geometry is going to matter that much. I really want to focus my time on building HVAC and air infiltration and other things. So we had a much more simple geometrical representation. He grouped all the windows together. And this is great when everybody tries something different, because we'll learn by contrasting results later on. So we have measured performance data in the building, and that's what the students are trying to predict. So here's, on one particular day, here's the measured air temperature inside one of the zones, one of the stories of the house. So that's the measurement, that's what we're going to compare against. And what we have over here, each of these lines over here, is a student simulation prediction. And we can see some of the predictions follow that measured data fairly closely, and others not so closely. So we try to understand why do we have differences here? This is not about pointing out a student's mistakes. It's about how do we learn from our experiences? How do we share that information with each other? So in this case, I asked the student who had this result with the red line here to show their work and discuss their approaches. And we tried to collectively develop an understanding of why they have such cold temperatures overnight, and then the building heats up, and their simulation heats up extremely rapidly. So we pulled that student's work apart and try to understand. There's different trial periods. So here's another period for a couple of weeks where the building is free floating, so there's no heating or cooling in the building. We're trying to predict the temperature distribution. Another trial where we're trying to predict the space heating load. So each of these bars here is a prediction of the space heating over a 1 week period. I've also got a culminating trial that's focused on HVAC system. This is what I'm adding to the second edition of the book. A number of the people who are using the book said they want more treatment on HVAC and more exercises of complex HVAC systems. So this is another building that I'm currently working on a series of exercises for. So we're focusing on the top story of this academic building on the campus. It's got an atrium space, and it's broken up into a number of thermal zones. Each of these is separately thermally zoned in the HVAC control system. And I provide, I'm working right now with a group at Integrated Environmental Services in their Glasgow office. I'm going through this exercise with them now. I provide them with building drawings, so they have dimension drawings. They have details on some of the wall cross sections. They have an inventory of all the materials that are used in the walls and envelope assemblies. And we're now focusing in this culminating trial on the performance of an air-based HVAC system. So this is a fairly conventional variable air volume system with an outdoor air economizer to minimize mechanical cooling, heating and cooling coils, a variable volume supply fan, VAV boxes with terminal hydronic reheating, so fairly conventional large building type HVAC system. And we're now going to try to predict through the simulation tools temperatures at various states within that HVAC system, the operation of the dampers in the VAV boxes, the operation of the hydronic heating systems. So I mentioned I'm working with IES in Glasgow. Here are some of their results so far. We're about halfway through this process, where we have the measured line here that is a regression of the daily heating load in that building over a winter period and versus the daily average temperature. And then we've got some simulation predictions here. So we have different simulation results that we're comparing against. And we're now at the stage where we're looking now at the details of what's happening within the HVAC system. So we're going to be predicting temperatures of outdoor air temperatures, return air temperatures, mixed air temperatures, either different state points in that HVAC, air-based HVAC system. This is examining the operation of the economizer cycle. So through this, it's a fairly extensive trial to go through, but it's really exercising the reader's ability to represent in their simulation tool a fairly conventional, detailed HVAC system. So this is the book that goes with the teaching method. It was published about 4 years ago, and I'm currently working on the second edition. I got to hand the manuscript to the publisher in October, so I'm going to be having a busier summer than I would like. And the major enhancements are more exercises, because that's the feedback I've had from my own students, plus the other universities that have used the book, is that they find that exercise is the most valuable part of the learning process. Students love to get their hands on the tool and start predicting things. And this guides them in doing that. So more exercises, the major additions to HVAC as well. So I'd be happy to take any comments or questions that you have on that.
Thanks, Ian.